Okay, we're going to continue on here, chapter whatever, 13 maybe. So last time we took quiz and we didn't get too far into the lecturing, but we did talk about how we manipulate equations and sort of the effect on the equilibrium constant values. So just a reminder that if you have an equation and you have a k value given to you, that k value, as we talked about, is specific for exactly how the equation is written. What's the reactants, what's the products. It's also specific for temperature, as we've talked about, I think, a couple of times up to this point. Temperature is really, again, the one and only thing that will change the actual value of the equilibrium constant when comparing against other temperatures. So we saw that in some cases you may be given multiple individual equations that have k values, and you may have to sort of build another equation from those and figure out what the k value is for that sort of built equation. So again, if we were to reverse a reaction, an equilibrium sort of reversible reaction, remember that what that actually does to the equilibrium constant is actually it inverses it. So you would take 1 over the k value. Again, here, we don't do any changing of signs like we do with delta H's. The relationships, actually, the reactants become the products become the reactants. So basically, everybody just flips in terms of the expression, and you basically take 1 over it. If you need to multiply by a common number across an equation, what that does to the k value is you basically would take that k to that number that you multiplied by. And again, if you just take a look again at the expression here for this guy, that is going to be our C times D divided by A and B. When we multiplied by 2 across, our k becomes C squared D squared divided by A squared and B squared. So again, the relationship here is actually, it goes to like the exponent. So if you had to multiply by 3, you would cube it for, fourth and so forth. And the last really thing that you would do is perhaps maybe you need to go through and divide by everything. So if you took this last one here and divided everybody by a common number, that would put us back to our original equation in this example. And again, that would give us that k value there, which is essentially the square root in this case. So you would take the square root of k. Again, if you were dividing by 3, you would take the cube root, or 4, the fourth root, and so forth. So those are very common ways to manipulate equations and sort of the effect that it has on the k value. The other real main thing as well that we talked about in terms of this is a very common mistake that people make is when they do add a number of equations together, again, to get an overall equation. Let's say that's K1 and K2. The K values are actually multiplied here and not added. So again, that's another very common mistake that sometimes people make. They add the K values rather than multiply them. Yeah. Yeah.
For to write it like the pressure, it would be like P2 P2.
It would be if those were all gases. If you're going to write a KP, you mean just the expression? That is correct. So when you're writing any equilibrium constant, and we're going to see a lot of them, we're starting to see a bunch of them, but it doesn't really matter if it's KC, KP, A, B, W, SP, all of them. They're all really just equilibrium constant expressions, and they're all products over reactants. So if there is gases, then that's what you would do, the partial pressures. And obviously, if you're dealing with concentrations, you would do the concentrations. Other questions? Yeah. Then let us continue here. So this again kind of summarizes what we just sort of talked about there on the previous slide. Again, for the most part, we want our concentrations to be in molarity. And I think we talked about it also a couple of times that if you're dealing with pressures, really atmosphere is the unit that you really want to use, especially with equilibrium type problems. as the question was just asked there, solids and liquids, again, are not included in the equilibrium expression. That, again, pretty much just leaves you, as we've been talking about, things that are aqueous and things that are gases get included. The equilibrium is just a number, as we talked about, really no units. And as we quote an equilibrium constant, it is, again, as I mentioned, specific for exactly how that equation is written and that particular temperature. And obviously, as we just talked about there, if we're going to add multiples together, you would multiply the K values here. Again, if we multiply, we're going to take it to that exponent. And if we divide, we're going to take the root of it. All right. K has the same value at a given temperature, regardless of the amount of reactants and products. And I think we talked about that as well. Again, temperature is the only thing that can affect us. But as we talked about, if we did a bunch of experiments, again, at 25 degrees Celsius, and you did a bunch of different experiments where maybe you started with some reactants, some products, some reactants and products, you should have the same K value all the way through for all those experiments. If you did the same reaction, say at 50 degrees Celsius, and you did like another, whatever, 4 experiments, you should have the same K value at 50 degrees all the way through. But in comparison between the two temperatures, you will have different values of K compared at 25 degrees versus 50 degrees. Everybody understands that? So that was the idea, what we talked about. I think I did something like, do we want to end up with a K value of 2, right? And we could get it by 4 divided by 2, 2 divided by 1, 8 divided by 4. There's different ratios, right, to give you the same sort of result. And that's what happens when we start with sort of different amounts of everybody. The reaction will always come to equilibrium at the same ratio of products to reactants. So you'll get that same sort of value as long as you don't change the temperature. Any questions on that there? So dare us talk about another letter just for a moment here. We'll go to our letter Q here and talk about something that's a little bit not really that different, but we'll talk about it. So Q is the reaction quotient, and Q is calculated the same way as we do K, which means if you wanted to calculate Q, you would take the concentration of your products divided by the concentration of your reactants. You would still do the exact same thing you do with K, which is take your coefficients as your exponents and all that. So everything pretty identical to how you would calculate K. So you may be saying, why do I need Q if I could just calculate K? The reason we typically use Q is really for a couple of situations. First off, maybe they're initial concentrations, or you're not sure if they're equilibrium concentrations. So really what Q will tell you is the first are you at equilibrium. So you could calculate Q and you could compare it to the K value for that reaction. And based on what you get, it will tell you, first off, if you are at equilibrium. So if you calculate Q and it is greater than the K value, you are not at equilibrium. And the second thing that Q will also tell you is if you are not at equilibrium, which way you need to go to reach equilibrium. Do you need to make more reactants? Do you need to make more products to reach equilibrium? So it will tell you which way you need to go to actually get to equilibrium. So in the case of Q is greater than the Kc, you're not at equilibrium. And to reach equilibrium, you actually need to make more reactants. So if you do set up Q on the left and K on the right here, it is opposite of where that sign is pointing. So it's pointing to the right. It needs to go to the left to get to equilibrium. If you calculate Q and it actually does equal K, then that means that that system is actually at equilibrium at that point. Now, if you calculate Q and it is less than K, it means you're not at equilibrium. And to reach equilibrium, you need to go to the right there towards products, and you need to make more products to reach equilibrium. So we use Q in a couple of situations. I call one situation just a straight up Q type question, which is this system at equilibrium? And if not, which way you're going to go? So that's like one type of place where we would use it. And it's just that question of, are these going to get us to equilibrium? And if not, which way we need to go? The second place that we calculate Q is when we are actually doing equilibrium calculations and we have the starting amounts of everybody in the equation. And that will tell us which way it needs to go to reach equilibrium, which can affect your equilibrium calculations. So we'll see that a little bit later on when we get to there. But that's sort of a separate sort of thing where you want to do that. Clearly, the only way that you're able to calculate Q is that you have concentrations for everybody, right? So if you're just given concentration of reactants, for example, there's no possible way to calculate Q because you don't know what the product is. So it's really a situation like that. If you see you're given the concentrations of everybody in the equation, you probably should calculate Q just to verify kind of which way the reaction is moving, because it can affect the calculation later on. But most of the time, probably it'll be more just a straight up Q type question of, is it at equilibrium? And if not, which way it has to go to reach equilibrium. And once again, Q is calculated the exact same way as you do K. And again, we still use our coefficients as our exponents. So why don't we try one here? If we are starting this reaction with 0.249 moles of N2 and some H2 and some NH3 in a 3.5 liter vessel. If the Kc is 1.2, is this at equilibrium? And if not, which way does it need to go to reach equilibrium? So take a few moments there to see what you come up with here. Okay, so let's take a look. So this would be what I would classify as just a straight type of Q type problem. It's really asking, is this system at equilibrium? And if not, which way does it need to go to reach equilibrium? The reason here is obviously we have kind of starting amounts of everybody in the reaction. So we don't really know if we're at equilibrium. These are equilibrium concentrations or what they may be. So that is what we're going to use Q to sort of help us figure out. So again, Q here is going to be calculated the exact same way as we would do K. So that's going to be our product. So in this case, our NH3. And we do want to square it because of the coefficient here. We're going to divide it by the concentration of our N2 and our H2. And once again, we're going to cube it because of the coefficient. So done exactly the same way. Here, though, we don't have the concentration, but we do have the moles and the liters. So probably that's the first thing we want to calculate is the concentrations of each of these guys. So for our N2, that would be 0.249 moles over 3.5 liters. And that's going to get us here, looks like 0.0711 molar. For our H2, we'll take the moles, which was 3.21 times 10 to the minus 2. We'll divide it by our volume here. And that's going to get us, looks like 0.00917. And lastly, we'll do the same thing here for our NH3. And in this case, we got 6.42 times 10 to the minus 4 moles over 3.5 liters. And that's going to get us there. I punch it in. There we go. I'll go 0.000183 molar. So now that we have the concentration of each of our guys here, we could go into our Q expression. So our Q would be our NH3, which would be 0.000183. We do need to square it, divided by our N2, which is 0.0711. And lastly, our H2, which is 0.00917. Remember, we also need to cube that guy as well. So if we do that, a little square action, a little 0.0711, and divided by 0.00917, that is cubed in this case. And at this point, I think you get something like 0.610 here is our Q value. First off, any questions on the calculation here? So now that we've calculated Q, we want to compare it to the K value that was given to us, which is 1.2. My Q value in this case is greater than, equal to, or less than K. It is less than K, yes. So because it's less than K, the first thing it tells you is we are not at equilibrium. And in order to reach equilibrium, it will go opposite of where that's pointing. So it will head that way towards the products. And we need to make more products to reach equilibrium. questions on that there? Yeah.
Earlier, when you put the K, it was like the square root. Is that why you're just squaring it?
No, so this is just the expression based on the coefficients from the equation. So if you're asking about the squares, because this is 2.
Like the K.
I'm not sure which one we're talking about. It might have been specifically for that example I was doing that we divided by 2, so we took the square root of the K, if that's the one you're talking about. Yeah, that's because we divided by 2, and when you divide by 2, the K value becomes the square root of it. Yeah. Yeah. Other questions? Good. All right, questions on Q. So again, this is probably a lot of times how you would use Q, but we will see it sort of pop up again here in the next sort of calculations that we are doing. So let us get into, dare I say, the calculation of the season here, which is this one, how we solve equilibrium problems. So when we are asked to figure out the equilibrium concentrations of everybody, or the equilibrium pressures of everybody, this is the calculation that we do, and this is pretty much the calculation we're going to do in a lot of places for a lot of things. So the idea of how we solve for equilibrium concentrations or pressures is we typically will use what is referred to as a ice table. Yeah. Now, maybe you used the ice table before or not. Sometimes people are taught limiting reagents with ice tables. Anyone? No? Yeah. I do when I teach that class. That way, when you get here, you know how to kind of do it. But most people don't. But we can use an ice table here. And ice means initial change and equilibrium. I'll write the whole thing there, but you get equilibrium. As I run out of room going underneath everything. There we go. All right, so we use this ice table to help us figure out basically the equilibrium concentrations of everybody. Now, we usually will have an unknown, and that unknown is basically X. And most of the time we use X in the table to represent the change that's occurring. And a lot of times what we're trying to find is actually the change in X. Then we use X to calculate basically the equilibrium concentrations, our pressures. So how does this work? Let me just do a really bad example here. No, I'm just kidding. I'm going to try this again. Let's see what we got. All right, so let's just say we have an equation like A plus B goes to 2C in this case, right? And let's just say in this case, we are given the concentration of A initially is, we'll just say 2 molar. And the concentration of B is 4 molar, right? And that's all we're given in this case. And what we want to figure out is what is the equilibrium concentrations of everybody when they reach equilibrium. So initially we would do our ice table here by putting on our initials, which would be our 2 molar here, our 4 molar here. Now, in a lot of problems like this little made up one here, we're not given anything about C. So typically, if you're not given anything about the products or something like that, it is safe to usually assume that you are starting with nothing in terms of the product side. So it is usually pretty safe to assume that. Now, the change part is really the important part of this equation and this sort of calculation. It does a couple of really important things when we're doing these calculations. The first thing we want to think about is what is happening in this reaction. Because in this particular example, we have no products to start with, we would expect this reaction to head in which direction? Towards the products or towards the reactants? Which way should this go? It should go towards the product because frankly, we have no product. So our only option is our reactants to come together basically to make products. That means as this reaction is taking place, would I expect are less of A and B? Less. And I would expect more of our products here, our C in this case, right? Because we got to use our reactants to make our products. So we should expect the reactants to come down and we should expect the products to come up. We represent that in the ice table with minuses and pluses. So in this case, this would be minus x, as we would expect it to be decreasing. This would be minus x, as we would also expect it to be decreasing. When we get to the product side, this is going to be plus 2x. Now, a really important thing here, as we know when we do calculations involving equations, is stoichiometry, right? And mole-to-mole relationship. So when you do the change part, it's really important that you always put the coefficient in there with the x's, because what that does for you is pretty much take care of the mole-to-mole relationship for you. So if you do not put the coefficients in there, you're going to have the wrong mole-to-mole relationship, and ultimately you're going to have the wrong answer at the end. So it wraps the stoichiometry part of it in with the kind of equilibrium part of it and the change that's occurring. So that's really important. You got to always include, and obviously we didn't include anything on the left-hand side because they are ones, right? So basically it's 1x. So we just write x in that case. So that's really important. At the end here, we would end up with 2 minus x, 4 minus x, and 2x, right? Now, this is good that we got to the equilibrium, and that's the equilibrium line of what everybody's concentration is going to be when we get there. We need to, in this case, basically figure out what x is, what the change is happening. And we do that by using our equilibrium expression. So in this case, this would be c squared divided by a and divided by b. And let's just say in this problem, k was, I don't know, 125. So this would equal 125. And obviously I just made that number up. What we would do at this point is we really want to solve for x. So we would take everything in the equilibrium line and basically put it into our expression. So all those guys are going to go into this expression here. So everybody from the equilibrium line is going to go into that expression. And that would give us, in this made-up example, something like 2x squared, divided by 2 minus x, 4 minus x equals 125. At this point, you're going to do some math, yes, and we're going to solve for x. Now, once we do solve for x, and there's a couple of ways that you could solve for x, I will say that probably the most complicated way that we will solve for x is to use the quadratic formula. So if you're not familiar with the quadratic formula, you would do a little factoring action right along here and get everybody into this general formula of ax squared plus bx plus c is equal to 0, right? That's like the quadratic sort of equation there. And that goes with x is equal to minus b plus or minus the square root of b squared minus 4ac divided by 2a. Yes. So this is obviously your A, your B, and your C. And obviously, if it was like a minus there, you would take the negative with you. Yes, sir. The X in the table is basically the change that's occurring. So it's basically how much, for example, reactants we're losing as this reaction takes place. And it's how much products we're gaining on the other side. Yeah. So if you use this quadratic formula, how many X's do you get? You get 2 x's, right? So if you use the quadratic formula, you get 2 x values, right? One doing it the plus way, right? And one going back and doing it the subtraction way there up on top, right? Now, when you do get these 2 x values, one of them, when you put it back into here, by the way, that is what x is, right? It is all this change all the way through here. When you put that x value back into the equilibrium line, one of them will give you a negative number, which, as we know, you cannot have like a negative concentration. So that would be not the one to choose. So you want to choose the one that's not going to give you a negative number. Now, just so you know, when you do the quadratic, you could get a positive and negative number. You can get 2 positive numbers and you can get 2 negative numbers. So, you could get any combination thereof. But what you're looking for to eliminate one of them is when you put it back, say, into there, obviously, if it gives you a negative number, or if you put it back into here, it gives you a negative number, that would not be the correct one to do it. Any questions on that? Yeah. Get to no, because one will typically be too big, for example, even though you got two positive numbers. So say, yeah, say like we have 4 minus x, so maybe you get like a 6. So you get 4 minus 6 will give you -2. So yeah. So one of them, regardless of what it is, and even the odd one where you get two negatives, it will work in certain situations. One of the negatives will actually turn into a positive in a certain situation, and it will actually work for you. But most of the time, you'll probably end up with like a positive, negative, and a lot of calculations. But it is possible to get any combination thereof. So this again would be probably the most complicated way that we would solve one of these. And there are some other ways that we'll talk about as we go through it. But ultimately, what you're trying to do is solve for x. And that's important because, again, once you get that x value, that is going to be, as I mentioned, all these x values. And now you'll be able to plug it into that equilibrium line and get the equilibrium concentrations if these were concentrations. So if we were doing a nice table here, molarity here is what we would be using for concentrations. This is the place where we were talking about earlier about pressures, that if you're doing an ice table, you need to make sure it's in atmospheres. So if you're doing pressure, works the same way. You just have a Kp versus a Kc value and just put the pressures in there rather than the concentrations. But they do need to be in atmospheres. And again, even if they give it to you in some other unit, you got to convert it into atmospheres, do the ice table, and then convert it back to whatever units you're looking for. Any questions on that there? Yeah. Say it one more time. If we were just giving.
Just give the molarity of product and not give the molarity of
Yeah,
reactant.
You could go backwards. Yeah. So this would be, speaking of that, this would be another situation where perhaps that Q calculation that we just did could come into play. So for example, let's say we were given concentrations of everybody, right? And that means that obviously this reaction is happening. We got stuff on both sides of the arrows. We would want to calculate Q to verify that the reaction is heading, say, to the products. If it wasn't heading to the products, or if, like the question was just asked, you were only given products, that would mean this reaction would actually head in which direction? It would head this way, right? So if we calculated Q and it said you need more reactants, or if you were just given products, the only way this one could go is to the left in this case, right? Which means when we get to the change line, right? That would mean that my minuses actually should be on the product side, right? And my positives would be on the reactant side. So to answer your question, yes, you can do that. And you would just have those guys switched in terms of which way it's going. Or that again is the other place where you should calculate Q just to verify, which way it's going, because it can affect the change part of it. Yeah. Other question? Yeah. You would actually when you factor all this part out and you get it all together in this form, you basically take the coefficients in front of all those guys, and that's your A, B, and C values, and you put it into here, and you get 2 because the first time you do the calculation, you do plus here. The second time you would do minus, and that would give you 2 different ones. Other question? All right, so let's take a look at one here together and see how I remember to do it. All right, let's take a look at this one at 1280 degrees Celsius. That seems very hot. We have a equilibrium constant value for this reaction of 7. If the initial concentrations of Br2 is 0.663, calculate the concentrations of these species at equilibrium. All right, so the first thing I'm going to do is going to write my equilibrium expression here. So my K is going to be my Br. Once again, we're going to square it because of the coefficient. We're going to divide it by the concentration of Br2. And in this case, it equals lucky number 7 here. We're going to definitely set up here an ice table to calculate this. And if you know nothing else in this class and you're not sure what to do, probably a good shot you should throw down an ice table in a lot of situations. Yeah, so It always amazes me when we do all these ice table calculations and people come to like an exam and they never do an ice table. I don't know why you would not ever not do that. So just think about that as you go through these things. We're going to do an ice table here. So we have only the initial concentration here of the BR2 given to us. Again, we're going to have nothing mentioning about BR's concentration initially. So it is, again, safe to assume that we're starting with 0. This also should tell us it's probably safe to assume that this reaction is going to head towards the product side since we have no products. That's going to help us with our change part. In this case, it's going to be minus x because the coefficient is 1. We should be increasing on the right-hand side, which means this will be 2x in this case. And again, taking our coefficients there on our change. That means when we reach equilibrium, we will have 0.663 minus x and 2x. Questions on this ice table here. So remember that our goal here is to figure out what x is. So to do that, we're now going to take our equilibrium line and we're going to put it into our equilibrium expression. So if we do that, that is going to give me 2x, and I'm going to square it, divided by 0.663 minus x equals 7 in this case. All right, so I'm going to do a little bit of math here. I'm going to take this entire thing on the bottom and I'm going to multiply it to the other side. And I'm also going to square the top part at the same time. That's going to give me 4x squared is equal to 0.663 times 7, 4.641 minus 7x. Now remember, we pretty much want to get everybody to the same side so we can equal this to 0. It really doesn't matter which way you move it, but I will say that most people will keep the x squared positive, but you don't necessarily have to, but most people will just kind of keep the x squared like positive. So that means I'm going to take everybody on this side and move it back over here, subtract and add appropriately. And that is going to give me 4x squared plus 7x minus 4.641 is equal to 0. This is my quadratic, right? That is my A, B, and C. So there is my A, there is my B, and with the negative there is going to be my C. Yeah, so you got to keep that negative sign there from the subtraction. Any questions on that there? All right, so we're good to go into our quadratic again, which is minus b plus or minus the square root of b squared minus 4ac divided by 2a. So putting that in, that's going to give me minus 7 plus or minus the square root. Now, if I put in all my values there into the square root, that will give me 7 squared minus 4 times a, which is 4, times c, which is negative 4.641. That will give me inside the square root something like 123.256. Now, if I take the square root, that will give me something like 11.10. All divided by 2 times a, which is basically 8, right? 4 times 2 in this case. Any questions on that so far? All right, so we're going to get our 2x values here. I'm going to do the plus first. So that's going to give me a minus 7 plus 11.10 divided by 8 will give me 0.513. I am now going to do the subtraction instead. So that's going to be negative 7 minus 11.10 divided by 8. Going to give me a negative 2.263. Questions on that? So remember that what we just solved for here in terms of our x value is all these x's we see in our table under the change part, right? So which one would not be the value I want to use? The negative, right? Because if I take this negative and put it into there, for example, I'm going to get a negative concentration, which you cannot have, right? So that means that really our correct X value that we want to use in this particular case is going to be the 0.513. So now that we have that, we can figure out the equilibrium concentration of BR2, and that would be 0.663 minus our X value of 0.513. And that's going to get us there a number 0.663 minus 0.513. There you go. Of 0.150, and this is molarity as it is a concentration. For our BR, that's going to be 2 times X. And we will get 2 times 0.513. I don't know, we'll call it 1.03 molar for that guy as well. First off, any questions on that calculation there? Yeah. I didn't use the negative value because when I would put that negative value into here, 2 times that's like -4, and you can't have a negative concentration, right? Or a pressure, right? So it's got to be a positive number. So that is how you know it's not the right one to choose.
You could still get 2 positive numbers.
It is possible. In a very rare case, you'll probably have 2 negative X values, but it can happen. And one of those, believe it or not, when you put it in, will actually give you a positive number. As odd as it sounds, because something there will be negative as well, so it'll kind of balance out. But I would say in most cases, probably 9 times out of 10, if you got like a positive and negative number, probably that negative is probably in the wrong one, and probably in most cases. But there is a small little rare occasion where you can get actually 2 negative values, and when you put it in, one of them turns into a positive value. Yeah, that's the right one. Yeah. So that's ultimately what you want to look at is when you plug those X values into the equilibrium line, you end up with positive numbers, right, for everybody. And if you end up with a negative number for whatever reason, when you plug that X into the equilibrium line, that would be the incorrect value. It's actually both. That's where the 2 originally came from, the coefficient. But ultimately, it's because at equilibrium, this equals 2 times the change. And so that's where the 2 comes from. And here we didn't do any multiplying because it's basically just minus X because coefficient there was 1. Right, so you got to do it in both places. So you got to do it in the ice table, take the coefficient into account, and you also have to do it like normal with the expression, take it into account as well. So you got to do both of those, yeah. Other questions? So this is math, right? Which means in most cases, one of the nice things about math is you could kind of check to make sure you didn't screw up in most cases, right? What could I do to check to make sure perhaps I didn't screw up? I have now the equilibrium concentrations, right? Which means if I put it into my equilibrium expression, those numbers, what number should I get? Around 7. We're a little bit off with some rounding, but you should be in the ballpark of 7. So you can actually put those values back in. So if you did that and you took 1.03 and squared it and divided by 0.15, you get about 7. And that's a good way to check yourself. So this is not super overcomplicated, it's sort of quadratic, but there are some where there's a lot of like numbers moving around. And sometimes at the end, it's probably a good idea to stick it back into that expression. And again, it may not always hit exactly, but it should be fairly close with rounding in the ballpark. If you're significantly off from the K value, then you probably made a calculation error somewhere along the way. Other questions on that? Well, I did one, so clearly it seems like you should do one. All right, do this one. We got a mixture of 0.5 moles of H2, 0.5 moles of I2 in a 1 liter flask. What is everybody's equilibrium concentration if the K value here is 54.3? Okay, let's take a look at this, see how you're doing. So again, here we have a mixture of H2 and I2 in a 1 liter flask, and we're looking for everybody's equilibrium concentrations. So perhaps here we will write our equilibrium expression. So that is going to be our HI. And again, we do need to square it because of the coefficient. That will be divided by our H2 and our I2, and that will equal 54.3. We do need our concentrations here. So these aren't too bad to figure out since we're dividing by 1 in this case. So 0.5 moles divided by 1 liter is 0.5 molar. And for our I2, going to be basically the same thing here, 0.5 moles divided by 1 liter gives us 0.5 molar. All right, so we now have everything that we need. I'm going to flip, I think, the screen here and go to the next page to write it, I think. All right, so still that. Perfect. We can do our ice table. So initially here we have 0.5. We have 0.5 of this guy as well. Once again here, we're not given anything in terms of the HI, so safe to assume that it's going to be 0. Also, this also means that we know the direction this should be heading is to the right-hand side. That's going to give us our minuses on the left and our pluses on the right. The change part here, minus x, and a plus 2x, once again, for the coefficients as well. That means when we reach our equilibrium, 0.5 minus x, 0.5 minus x, and 2x. Any questions on the ice table there? Yeah. I did because I think they had 3 significant figures. Yeah. Other questions? So like we talked about at this point, the goal here is to solve for x. So we're going to go into our equilibrium expression there that we wrote last time, and that would be 54.3. So putting that into this expression gives us 2x, and we're going to square it, divided by 0.5 minus x times 0.5 minus x is equal to 54.3. At this point, we do want to solve for x, and hopefully you look at that and see it is a perfect square on both sides. So you don't necessarily have to do quadratic unless you're fond of it. You could do it if you like. You could always do quadratic if you like to, but this actually is a perfect square on both sides, which might be an easier way to solve for this. So that should give you 2x on top, should give you 0.5 minus x. And the thing I always personally forget to do is actually square root of 54. So let me do that there before I forget. And that will give me 7.3689, we'll call it. At this point, we can now multiply this to the other side. And if we do that, that will give us 2x is equal to 3.6844 minus 7.3689x. We're going to take this guy and add it to the other side. And that's going to give us 9.3689x is equal to 3.6844. Do a little dividing back this way, right? And that will get us 93 to 9.3689. Going to give us an x value here, in this case, is 0.393. Questions on that? Now, if you did the quadratic, you should ideally, with rounding, end up pretty much in the same spots. So you can always do the quadratic if you like. At this point, that is definitely going to be our x value, and we're going to put it into each of these spots here. So that means that the concentration of H2 will equal 0.5 minus 0.393, and that's going to get us 0.5 minus 0.393. 0.107 molar. For our I2 is pretty much going to be the same thing. 0.5 minus 0.393 equals 0.107 molar. And lastly here, our HI at equilibrium will be 2 times x. So we'll times that by 2. 0.393 times 2. 0.786 molar in this case. Any questions on that one there? Once again, if you put these numbers back into our equilibrium expression, you get about 54, which is good. And again, that's a good way to check yourself. So this is another way that you could solve these type of problems. If you get lucky enough that you have a perfect square on both sides, take the perfect square opportunity, yes, and save yourself some headache, perhaps in the calculation. Not always going to work, obviously. Sometimes you do got to factor it out, go quadratic, go old school, huh? Any questions on that there? Well, then let's get to one where you're going to have to do that. So this one, here we go. Have fun. I'll see you in 20 minutes. All right, so do this one, same equation, same K value, but in this case, we're actually starting with 0.00623, 0.00414, and 0.0224 of everybody. What are the equilibrium concentrations? Take some time, see what you get going on this one.